Hello, this is Jack Jackson, and today we're going to be looking at an investigation of Chebychev's theorem. Now, Chebychev's theorem gives us a way to give a measure of relative standing, sort of, that is based on knowing the mean and the standard deviation. It's also related to z-scores, so we're going to talk a little bit about z-scores and Chebychev's theorem. Now, to do this investigation, we're going to look at this sketch here. Now, hopefully you've already remember seeing this particular sketch in an earlier video where we looked at a way of finding the standard deviation and understanding what it meant. So remember, standard deviation, we found the mean, which is represented by this red line right here in the middle, and then we use this formula here. We found the deviations from the mean. We found the deviations from the mean, and then added those up, squared them first, then added them up, then divided by 1 less than the sample size, and then square root for the standard deviation. And so in this case, the standard deviation at this moment is 3.15, and that's represented by this, the distance of this little orange bar right here that says 1s on it. So in other words, the distance from the red mean line to the line, this orange line here, is 1 standard deviation. So this x value down here on the red line is 17.65 at the moment. That's the mean. And this value right here where the orange line, the one on the right, hits the axis, is x bar plus 1s. So right now that would be, I guess, 17.65 plus 3.15. What is that? 20.8. Okay, and this orange one over here is 1 standard deviation below the mean. Now, what I want you to notice is there's a lot of data that's here between these standard deviations, between 1 standard deviation above and below the mean. So if we look at the interval from the mean minus 1 standard deviation up to the mean plus 1 standard deviation, let's actually go down here and compute the frequency of points that are in that interval, and then the relative frequency of the points in that interval. And then we'll do the same for going out 2 standard deviations and 3 standard deviations. And luckily I have all of these marked on the sketch over here. So if we look back at our sketch, we're seeing the things that are within 1 standard deviation of the mean, that is from mean minus 1 standard deviation to mean plus 1 standard deviation, are the dots that are inside the 2 orange stripes there. So let's just count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And that's out of 16, 17, 18, 19, 20. So there's 20 points in our data set. 15 of them are in that interval. Okay, so 15 are in that interval. If we, let's see, we can make a percent. If we just multiply this by 5, that's 75% of the data is within 1 standard deviation. Okay, let's look at within 2 standard deviations. Well, we got those 15, plus we pick up another, these 3 and this one here. So now we're up to 19 out of 20. So 19 out of 20, and that's actually 95% of the data. And within 3 standard deviations, not quite, that one's just outside of 3 standard deviations. So remember back here, so the orange bars are 1 standard deviation away from the mean. The green ones are 2 standard deviations of the mean. So when we counted these, all of these here, and found that 19 of the points are between the 2 green stripes there, then we're between this x value of mean minus 2 standard deviations, and then this one over on the other side, which is mean plus 2 standard deviations. If we go 3 standard deviations out, then we're going the brown bars. Notice that these bars are all equally spaced. The distance between them is 1 standard deviation. So we go 1, 2, 3 standard deviations to the left, 1, 2, 3 standard deviations to the right. We almost pick up everything. This one's just outside that. So again, in this particular case, we're still picking up 19 standard deviation, 19 points, or 95% of the data. Now what I want to do now is see what happens if we move some of these points around. So if I move a point, say a dot plot over here, now I actually moved it from inside 2 standard deviations to outside, but notice at the same time it increased the standard deviation too, so that these bars are wider. These intervals are wider. So now let's see what happens now. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We still got 15 in there, but now we have only 18 out here. So it didn't change that, but we did change, let's see, we did change this and this one. Let's see what that does to us. So we changed this to 18. I believe we have 2 outside the green bars. But now we've got everything, all 20, inside the 3 standard deviations. That's kind of interesting. So we've got all 20 here, which is 100%, and we ended up with 90%. So we were able to decrease the amount within 2 standard deviations, but we actually, at the same time, we ended up increasing the amount within 3 standard deviations. Now notice that didn't make this point over here, this one over here, any closer to the mean. I'm not sure. Actually, it made it a little bit further away because the mean actually moved to the right just a little bit. But what it did was increase that length of that standard deviation, so that got wider. So we actually picked up more. So let's see what we can do here. And what happens if I kind of spread out this data a little bit more? What happens to the picture now? Well, within 1 standard deviation, now 1 standard deviation is much larger now. 1, 2, 3, 4, 5, 6, 7. We did decrease it though. We went down to 13. So now we've gone down to 13. But these are going to change too. So we went down to 13 here, which is 65% within 1 standard deviation. We also, within 2 standard deviations, now let's see, that's going to be out to the green bar. I can see it here. Can I see it over here? There it is. And so, okay, I think we can see all the points that are within there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 points. Actually, that's all of them. That's all 20 within 2 standard deviations. There's nothing out here. So we actually got more. Of course, 20 are within 3 standard deviations because they're within 2. So we end up getting 100% there, even though we have less within 1 standard deviation. Okay, let's experiment a little bit more. What if we make this kind of, let's do it like this. We're going to stack a lot of points on one end. And then we're going to have a few points kind of spread way out. So most of the points are going to be in close together. And then they're going to let's have a couple of points that are way out there. Let's stack up a whole bunch of them right here. Okay, now we have lots of data within 1 standard deviation, and all of it's within, well, no, there's a couple that are out here, but not much beyond, nothing beyond 3 standard deviations. So the point is, I can experiment with this, and I can see what's going to happen with these different possibilities for how spread out this would be. But one of the points is as I spread my data out, they get further away from the mean perhaps, but they also have a tendency to look what that does when I bring it out. See, it makes that standard deviation a lot bigger as well. What if I bring one way out here? Can I get even more out here? Let's see. There we've got 3 outside of 2 standard deviations. Can we bring it all the way outside 3? See, again, the problem is when you try to bring it out there farther, what happens? That standard deviation gets bigger to sort of compensate. So we can actually decrease these relative frequencies. Okay? We could possibly get all of the data in pretty close within 2 standard deviations. We were able to do that already. But could we spread it out some or fix it somehow so that the data gets more values outside, out here past 3 standard deviations outside of that? So to make these numbers here lower. Well, the answer is yeah, we can get them lower, but there's only so far down they can go. And there's some limit to that. And it turns out there is a worst case scenario. And the worst case scenario is basically, I'll show you what they are right here in just a minute. This is going to be the worst case. In other words, worst meaning the least percentage of data in the interval. And Chebychev's theorem is going to tell us what that value is. Okay? So notice, however, this is how many standard deviations we're away from the mean. So I'm going to call that number k. So here we're 1 away, 2 away, 3 away. Well, Chebychev's theorem says if you're going to look between x bar, actually let me phrase it in terms of the population. Okay, but it works for a sample too. You take mu minus k standard deviations up to mu plus k standard deviations. Okay, or for a sample that would be x bar minus ks to x bar plus ks. And what we're going to find is that at least 1 minus 1 over k, that fraction, square the k, 1 minus 1 over k square, that fraction of the data is in this interval. So let's work this out. Well, 1 minus 1 over 1 square is 0, so it actually is possible to make a data set where nothing is within 1 standard deviation. It's kind of difficult to do that. It's extremely difficult to do that, but it is actually possible. But that's so basically Chebychev's theorem tells us nothing about what's within 1 standard deviation. But notice if you go out 2 standard deviations, 1 minus 1 over 2 square, that's 1 minus 1/4, that's 4/4 minus 1/4, that's 3/4, or 75%. So 3/4 or 75% has to be there. Now notice we had 100%, we had some other different values, but you'll never get below 75%. Now oftentimes it's higher, maybe even as much as all the data is within 2 standard deviations. Okay? And many times it's way up there above 90%. But at least 75% is there, no matter what the distribution looks like. And then let's do out 3 standard deviations. 1 minus 1 over 3 square, that's 1 minus 1/9, That's 9/9 minus 1/9 is 8/9. So this is 8/9 or 88.8 repeating percent of the data. At least that much has to be within 3 standard deviations. In this case, of course, we got 100%, but it doesn't have to be that high, and we've already seen some where we had some points outside of 3 standard deviations. But you've got to have at least about 89% there, 88.8 repeating percent. Now, I haven't actually seen this data set, but I'm told that there is a data set that actually hits these percentages. So if it really does, then this definitely is a sort of a worst case scenario, that it actually hits that sometimes. But most data sets are going to have much more, obviously a lot more than 0% within 1 standard deviation, and even more here. If you notice the examples we did, we couldn't get it down to 75 or 88%. Let's experiment a little bit more. I'm not even sure what it would look like to make that happen. What if we had a lot of data here, really, really close, and bring these in small? So we've got our right now we have our standard deviation is really small. And what if we now take a point, try to bring them outside of the 2 standard deviations? Can we do that? Let's see what happens. Well, there we have 4 of the points outside of 2 standard deviations. A whole bunch within 1 standard deviation, but we have 4 outside 2 standard deviations. So what would that change our numbers to over here? So in this case we had 20 within 3. We had all but 4 within 2 standard deviations, so that's 16. And then actually all 16 of those were within 1 standard deviation. So what does that work out to be? That's 80%. Okay, so 80% of the data was here. Well, what are we guaranteed? We're guaranteed at least 75%, so we're getting fairly close to that. But notice when we did that, we ended up getting 100% of the data here, where we're only guaranteed about 89%. So, depending on the data set, these values can vary quite a bit. However, they are these are sort of the worst case scenarios. Okay, so what can we do with this, for example? Well, let's suppose we know the mean and the standard deviation of a population, or let's just say it's for data, for a sample. So the mean, let's say, is 15, and the standard deviation of the sample is 2. Okay, let's figure this up. How much of the data, what percentage, what fraction, we'll do the percentage, how much of the data is between, and let's go above and below that, let's go 15 minus 3 to 15 plus 3. Okay, so let's just say, instead of between, we'll say it's in this interval. So in other words, that's the interval from 12 to 18. So there's our 3. So the question is, how many standard deviations is this above the mean? Okay, it's the same amount above and below the mean, but how many standard deviations is that? So we need to take that, or we can do it, let's just start with these. We want to find what's called a z-score. Now remember, a z-score is you take the data value, in this case maybe the 18, let's take that in. Okay, that's our x. And we want to subtract the mean. Well, that's the 15. And that's our 3 that we already knew what it was going to be. And we want to divide that by however many standard deviations we have, by 2. So if this was just 2 away, we would know we were 1 standard deviation. If it was 4 away, we'd be 2 standard deviations. We're 3 away, so we're actually at 1.5 standard deviations. Well, this is the k that we had in Chebychev's theorem. Since we don't know anything about this particular distribution, we can use Chebychev's theorem. And we know that they're guaranteed to be at least 1 over 1 minus k squared. So this is 1 minus 1 over 1.5 squared. I'm going to use a calculator here. 1 minus 1 divided by 1.5 squared. And that is 0.5 repeating, or 55.5 repeating percent. So at least 55.5% of the data is in the interval from 12 to 18. Now most likely it's going to be higher than 55%, but at least that much. That's the worst case scenario. It is possible to make up a data set where you get exactly this percentage with this information in talking about that interval. Okay? But most data sets are going to have a higher number than that. So this is a worst case scenario. Okay? Let's do the backwards kind of problem, the reverse problem. So let's give a mean. Let's say it's 52 and a standard deviation of 4. What interval is guaranteed to have, let's say to contain at least, and let's give it a percentage of the data. Oh, let's say 60%. Okay, well we can use Chebychev's theorem here again. Okay, so we know that 1 minus 1 over k squared is going to be this 60%. Okay, of course we make that 0.6. And we can solve this for k. K is going to be basically our z-score. Well, no, K is not. K is going to be how many standard deviations we go above and below the mean. Not quite the same as the z-score. So we're going to, let's see, I'm going to subtract 1 from both sides, so that makes this negative 0.4. Multiply by negative 1, get this, rid of the negatives, decimal. Reciprocal both sides, so k squared is 1 over 0.4, and so k then is the square root of 1 over 0.4. I'm just going to use the calculator again. Parentheses, 1 divided by 0.4, and then square root all that. Let me just do it this way. Do the square root first. Square root of 1 divided by 0.4. Close. Enter. There we go. So k was 1.5811. 380 could be. Let's say it's about, that's approximation anyway. Let's say it's about 1 point. Well, we'll leave it like that. We won't round off. We won't round off until the end. That's always a good thing to do. Wait till the end to round off for any problem. Now, so what interval is? So this interval then, remember, needs to be from x bar minus ks to x bar plus ks. Well, x bar is 52, and then we go minus this k, 1.581138883, times the standard deviation of 4, and then the same up to 52 minus the 1.58, etc., times 4. Okay, I ran out of room there. Let's go ahead and work this on the calculator. Now that's my number there. So I'm going to actually take that number and I'm going to say store alpha k. So now if I just go alpha k and hit enter, it'll be that number. If I do 2k, it'll double that number, and so forth. So what I want is 52 minus k times s, which is 4. And this is going to give me my low end, which is 45.675. And we had some 4s there, 3 4s and a 6 8. So as far as this calculator will go, that's what we get. Of course, we'll round off a little bit. And then we can, now watch this, is a nice little trick with the calculator. Go second enter, and it gives you the same entry you just did, and we just need to go back and change that to a plus. So that's 58.324. Some 5s and a 3 2. Oh, let's just round it off. So 45, let's say 0.7 to 58.3. So that interval is guaranteed to contain at least 60% of the data. Guaranteed to contain at least 60% of the data. Okay, by Chebychev. And notice theorem. And notice that we did not have any information about what the distribution looked like. Now, oftentimes the distribution, as we saw, is going to have a lot more data that's there close to the mean. Okay, and a lot of times the data is symmetric, like this is almost symmetric here. And a lot of that data is up close to the mean and not so much spread out from the mean. When that case happens, we get a curve that is more like what's called a normal curve. Okay, I can show you a normal curve here just a second. We're going to study a normal curve a lot in the future, but this is what a normal curve looks like. Here's one standard deviation here, and if you're within one standard deviation, let me fix this. So the standard deviation now is approximately 1. So if we go here, we're going out one standard deviation. The mean is going to be 0. And we go one standard deviation above and below the mean. Okay, we're going out to 1 here and 1 here. And so think of your dots going up to the top of this curve here in your dot plot and being very closely spaced together. So you'd have a lot of dots right in here. Less here, and even less out here. Okay? Now, if it is from a normal curve like this, then it turns out that you get a lot of data close to the mean. Oh, that's a sorry normal curve. Let me try again. I can do a better job than that. Also, this is why I use technology. Okay, so we got the mean here. We got one standard deviation above and below the mean, say to here. There's the axis. And so this is the mean plus 1 sigma, mean minus 1 sigma, and it turns out that this is about 68% of the data. Well, if we go out another standard deviation, say to here and here, this is supposed to be symmetric, okay, and then do all the data here, including that 68% in the middle, now we're over 95%. And if we go out 3, so that's 2 standard deviations. And if we go out 3, all of this, 3 standard deviations, we're over 99%. Okay? And so the sometimes when you have a data set that looks like this, you're going to have your data values much more closely fixed up to this. So remember, this is like it with our Chebychev's theorem. We had k, 1, 2, and 3 standard deviations. Well, the minimum that you've got to get within that is, well, 0% here, so we know nothing about 1 standard deviation. For 2 standard deviations, it was 75%. 3 standard deviations, it was about approximately 89%. Well, for a normal, this is for any distribution, minimum, and for a normal, it was more like 68%, 95%, and 99%. Okay? And so sometimes your book will talk about the empirical rule. The empirical rule assumes that we have this normal curve. Here's what a real one looks like. It has a normal curve like this. It assumes that that normal curve is what's actually happening. And so the empirical rule assumes that. So if the data is close to normal, mound-shaped, kind of mounded up in the middle, pretty much symmetric about the mean's right there in the middle, so the mean, median, mode are all about the same thing, then going to be, and it's symmetric, okay, mounded up in the middle, then things are going to be a lot more close to the normal. So the empirical rule is actually not as hard and fast a rule as the Chebychev's theorem. Chebychev's theorem is absolutely dead on perfect every time, but it's a minimum. It's not saying that this is what you actually have. It's saying you can't get lower than this. Whereas the empirical rule is saying, you got approximately this much because you're approximately this normal curve over here. So hopefully that kind of clears up a little bit about what's going on with the empirical rule, Chebychev's theorem. And a little bit about z-scores. Remember, z-scores were you take an x value, you subtract the mean, so that right there is how far you are from the mean, and you divide that by the standard deviation. That's going to tell you how many standard deviations you are away from the mean. If the z is positive, you're on the right, and if z is negative, you're going to be on the left. So if this is 0 here for the mean, this is a z equals 1, this is z equals 2, this is z equals negative 1, and this is z equals negative 2. So negative z values are below the mean, positive z values are above the mean. And this would be a z of 0 if you're at the mean. Okay? And of course for a population, I guess I can use a capital Z for that, would be the x value minus mu over sigma. Okay, hope that was a little bit of help on investigating Chebychev's theorem.